derived. So that SI system considers 7 units of measure as base units. What are they? We've got base units of measure. We've got meter, kilogram, second, Kelvin, mole, ampere, and candela. These are 7 base SI units of measure. Physical quantities they measure. So pay attention here. This is not mass, but unit for the length, meter. One and the same symbol is used, but completely different thing. So the quantities which we use, this is length, mass, time, small t or capital T. So usually small because K is what the unit for the absolute temperature, also called Kelvin temperature, capital T. So measure of quantity of material, current magnitude, and since candle is the unit for the light intensity, to distinguish it from the current magnitude, we write here IV, being intensity of light. So current magnitude and intensity of light. So 7 base units of measure and 7 physical quantities being measured. So all other quantities, so we've got many other quantities. We measure them using combination of those 7 base units of measure. And they are called derived units. So 7 base and they are called derived units. Example, since we mentioned energy, energy's symbol capital E, unit of measure, as I've told you, is the joule. And let us show what is joule in terms of base SI units of measure. Energy, as we have already defined it, is the capacity of doing work, which means that if a system or an object has got energy, it can perform work. And work in mechanics is defined as force times displacement. I'm going to write it in this way. Sometimes delta, symbol for the change in location, we substitute by the symbol for differential. So thus, the unit of measure for energy being joule is, so having in mind the formula, force measured in Newton, distance in meter. So, but Newton is not base SI unit of measure. Newton, how to know what, so let me just write this once again, because not written well. Newton meter. So Newton is the unit for the force. That's why force must be defined in mechanics Second, Newton's law defines acceleration in an equation regarding its relationship with the force. So that force is mass times acceleration, which means that Newton is mass is measured in kilogram, acceleration is measured in meter per second squared. And in this way, we can substitute Newton in the expression for energy unit. So thus we've got kilogram, I'm just rewriting, meter per second squared times meter. So thus joule is kilogram meter squared per second squared. In this way, we can express any derived unit in terms of base SI units. So all those things which we have discussed, so let me just clear a bit to write. SI system international, and also known as SI system, also is known as MKS system, coming from meter kilogram second, the first letters of the three words showing units of measure. Meter, kilogram, second, and instead of SI, we may say MKS system. It is one and the same. So let us now proceed with the cancelling units. Cancelling units, number 3. Cancelling. So, in question mark, cancelling units. So, just to clear the board, when multiplying or dividing two or more physical quantities, it is permissible to cancel units that appear both in the numerator and the denominator of the combined quantity to find or to derive the new unit. So let me provide an example for cancelling units. There is a law in physics known as Stokes' law, which is about a force experienced by a spherical object moving with a certain velocity through a fluid of a specified viscosity. So thus the force is 6 pi r eta v. 6 pi constants, pi being what? 22/7 or 3.14. R is the radius of the spherical object. Eta is the dynamic viscosity coefficient. V is velocity. So let us now express the unit of measure of force. 6 pi, no unit. Radius is measured in meter. Viscosity, I'm going to write below. I'm giving it directly Pascal second. Pascal is Newton per meter squared second, since Pascal is the unit for pressure. So thus, let us substitute this here. Newton per meter squared second. So thus, this is unit for R. This one is unit for eta, being dynamic viscosity coefficient, and velocity, which is measured in meter per second. So thus, this is velocity unit. So it is permissible to cancel unit that appear both in the numerator and the denominator of that combined quantity. So thus, meter can be cancelled with second power, and this left meter with meter here. Second can be cancelled with second, and what is left? Newton, which is the correct unit for the force. So thus, the conclusion is we can cancel units, equal units, which appear both in the numerator and the denominator of some combined quantity. Then, next thing, let it be method of units for determining equations. So method of units for determining, for finding, for checking, for determining and checking equations. So let me write, and we'll focus on the check. That's why method of units for checking. Let us write just checking equations. Equations or formulas, which is one and the same. A quick check, which can enable to find errors in a formulation, in an equation, is to compare the unit of each term, and they must be same. So let me take an example. Let us write the total energy of a rigid object. So we know in physics there are two main types of energy, kinetic and potential, which means that the total energy is the sum of those two. So thus, let us write total energy being the sum of kinetic and potential energy. Further, kinetic energy we couldn't write previously, but now we can write kinetic energy, I told you, half mv squared. Potential energy, we mentioned gravitational energy being a kind of potential energy. Gravitational potential energy, product between mass, acceleration of gravity, and height, h, or depth, according to some reference level. So thus, let us rewrite. Rewrite here, half mv squared plus mgh. So, is this correct? Suppose we are not sure, is it correct or not? But we can check using units. So thus, each unit of each term must be same. Left-hand side unit, energy, this we wrote. Joule, being kilogram, you can find, previously we wrote, I'm not going to repeat, meter squared divided by second squared. This is the left-hand side term unit of measure. Unit of measure of the first term. Half is constant, which means dimensionless. Mass is measured in kilogram. Velocity is measured in meter per second, but second power. Second, 2, which is kilogram, meter squared per second squared. Same. Then the unit of the second term on the right-hand side, mgh. Mass is measured in kilogram. Acceleration of gravity, as any acceleration, is measured in meter per second squared. This is 2, not very well visible. So 2. And h is measured in meters. So thus, again, same. Kilogram, I'll write it here, kilogram meter squared per second squared. So thus, each term in a correctly written equation has got one and the same unit of measure. Let us proceed with the order of magnitude, but also with multiples and submultiples of units. So let me write number 5. Multiples and the submultiples of units. So, scientists often deal with very big or very small numbers, which numbers are difficult both to read and write. However, through the use of mathematical rules of exponents, those numbers can be written in very simple way. Example, the mass of the Earth, it is very big number. So let me write it. But before that, let me clear the board. So mass, I'm going to use this capital M, and E from Earth is 6, 0, 0, 0, 24 zeros. 24 zeros for not writing them, kilograms. Exceptionally big number is the mass of the Earth. So let us now take a very small thing or object such as an electron, which is a particle, as you know. So mass of electron is 0.0030 zeros, 9 there are more numbers, but for the purpose of discussion, not necessary to write them, kilograms. You see that not easy to write or read those numbers. To write them easily, we use a method which is called scientific notation. In scientific notation, numbers consist of non-zero digits to the left of the decimal point and the positive or negative exponent. This is the way we write in science big or small numbers, which, as I've told you, is called scientific notation. So thus, mass of the Earth, how to write it using scientific notation. We need to shift the understood decimal point, this is understood decimal point, to the left in the original number until a single non-zero figure is left. So thus, how many positions? 24 positions. So thus, we've got 6 times 10 number of places shifted, 24 kilograms. So thus, this number is the same as this one, but written more compactly, more easily. 6 times 10 power 24 kilograms. About the mass of electron. So we need to move the decimal point to the right in the original number in the same way until a single non-zero figure is left. So thus we've got 30 positions here plus 1, 31, which means that we have to write 9 times 10 power minus 31 kilogram. So this is the mass of the electron, written in scientific notation. So, frequently, it is exceptionally useful to compare numbers in terms of their order of magnitude. What is order of magnitude? Let me write those words here. Order of magnitude. Order of magnitude, definition. Order of magnitude is the numerical approximation of a number to its nearest power of 10. Numerical approximation of a number to its nearest power of 10. So thus, how to approximate this number for the mass of the Earth to the nearest power of 10? We know that numbers above 5 are taken approximately as 10. Below 5 as 1. So that 6 is above 5, which means that we can approximate it to 10. 10 times 10 power 24. So thus, but see, I'm not going to use sign of equality, but of approximation. Approximately 10 power 25 kilograms. So thus, if there is a question, what is the order of magnitude for the mass of Earth? The answer is 10 power 25 kilograms. So to express the magnitude just in terms of powers of 10. What about the number, the mass of electron? 9, approximately again 10, times 10 power minus 31 is 10 power minus 30 kilograms. So thus, we've got order of magnitude, useful way to compare quantities, their magnitude, useful way. And often scientists, as I told you, deal with very big and very small numbers. It is not good, for example, to express distances between towns in meters. Why it is not good? Because numbers are very big. Instead, one uses kilometer, in which kilo stands for what? For 1,000. Kilo being prefix kilo, written as small k, which is 10 power 3 or 1,000. This we may have kilo newtons, kilo amperes, kilo candles. So kilo can be added to any unit of measure, but not just kilo. Frequently, you see table of prefixes, different one, useful to deal easily with big or small numbers. So that we may even say kilo bicycles, which means 1,000 bicycles. Not popular in everyday life, but is possible, which means that kilo means just thousands, nothing more. Don't mix it with units of measure. So let me switch on the presentation, which, as I told you, is short, but и няма хъп, разбираш ли, аз сега не мога да приключвам автоматично, както и да е, да. Sorry for the interruption. See, you see the topic. In the first slide, we will just in a moment proceed with prefixes, but since we have opened the presentation, let us see what is given. I told you about this. I haven't told you about medicine because it is given here and we can see. Natural physics is what? It is a branch of physics, which in which physics, with its main concepts and laws and theories are used for the sake of what? For the sake of diagnostics, treatment, and even prognostics are given here. And even prognostics means also to prevent, if possible, non-desirable situations or outcomes to occur. Additional areas of medical physics. So we've got radiotherapy, nuclear medicine, and health physics. Those three main areas. And below, in yellow, you can see the most important applications of physics in clinical medicine. By we will study that one by one in different topics. Although we will very shortly study different imaging techniques. We'll study ultrasound more extensively. We'll study electricity and magnetism. Also the functioning of alveoli in the context of a trace wall, and so on, for not losing time. And here in this slide, the aim is to tell you that all the processes that occur within a living system, so they can be quantified using physical tools. Absolutely all day. There's not an example in which, until this moment, in which this cannot be done. And we reached what we were talking about. Prefixes. See, all those prefixes you have to learn by heart. For what purpose? For being able, or just to close the microphone, for those who are not here to listen, but this is important, prefixes to be memorized. Why? For being able to pass physics and biophysics exam, since in both exam papers there are the so-called conversions of units. And now I'm going to demonstrate them. How to change units from a unit with one prefix into a unit with another prefix. Prefix or prefix. Okay. So we just mentioned, sorry, I don't have pointer because of some other reason. I'm not going to discuss kilo, but you see all day. And what to mention here? This is the boundary between positive and negative exponent. All prefixes will positive exponent represent big numbers, and with negative small. As you have seen on the basis of what example? Mass of electron and mass of the earth. Those two examples of big and small mass. So that's. Let me now show you. So let us have just 10 minutes break. The big function should begin exactly after 10 minutes. Since what is left today to show you conversion. So significant digits I will discuss shortly. You will study since rules are given here, but also we need to discuss some formulas regarding accuracy of measurements in terms of absolute and relative values. So those things. So that's why potential work is waiting. Okay, 10 minutes break. Things which we discuss here inside here this is an audio lecture covers module 1. Thank Can't hear you. What about lecture notebooks? Everybody including students online must upload them. And if they cancel themselves, they will have to be here, prepare everything to be in the proper way. Oh, absolutely physical everything. That iPad is anonymous. You may tell you that it is yours, but it can be used by anyone. No. So iPad for you, not this. Real physical papers. And here's that second sheet papers only because we just have experience with chips. Never use. Do not use. Okay, because you use it on time. Not from now on. Cancel. No problem. This is good. Good. Real. I understood we don't have which are expressed by Okay, so let us begin with some conversion. So let me demonstrate to you what you need to know obligatory, and by there are many examples in the red practice book. That's why you can practice there and check what you know and what you do not know. So let me take some example, imaginary. So now I'm going to invent it. Suppose you've got a length being, just to change the color. Suppose you've got length of some table, for example, being so 1.2 meters. So the question is, change this into, for example, kilometers. Is it possible? Of course, yes. And how to do this? Initially, we've got just units to consider. Let us see 1 meter, how to change into kilometer. So looking at the table, kilo is 10 power 3. But those powers here, or exponents, whether they positive or negative, this depends on the specific situation. And we've got now small unit, smaller one, to be changed into bigger unit. In this case, the exponent is not positive but negative. So that's why let me write here negative exponent, minus. So 1 meter is 10 power minus 3 kilometers. Since it is 1 kilometer, not kilogram, mistakes do happen. Kilometer. However, if you needed to change kilometer into meter, which means big into small, then the exponent is positive. So thus we can write 1 kilometer is 1000 or 10 power 3 meters. So thus this is important things to understand, otherwise solutions won't be correct. So thus, to come back to this very example, 1 meter is 10 power minus 3. That's why we'll write here 1.2. Instead of meter, we'll write this times 10 power minus 3 kilometers. This is the solution. Now, let us have another example. Let us have some length being smaller one. Suppose we've got 0.0034 micrometers. This to be changed into nanometers. Micro into nano. Let us see the table. Micro, given here, as 10 power minus 6 given, but I told you regarding the sign. It can be minus or plus depending on the specific example. Big into small or small into big units are to be changed. So thus, exponent here is 6 in micro. In case of nano is 9. Micro is bigger unit than nano, obviously. Since 10 power minus 9 is point and then 8 zeros, 1. In case of 6, point and 5 zeros, 1. So thus 3 zeros more. 1,000 times bigger is micro than nano. So let us now, to clear this, let us now do this. Initially dealing with the units. How to change 1 micrometer into nanometer. So we'll write 1 micrometer is 10 power what? Minus 6 meters. So small unit, big unit. That's why negative exponent. However, we don't need meter here. Nanometer is needed. That's why, let me write just below, 1 meter is. Meter is bigger unit than nano. It is 10 power plus 9, that's why positive, nanometer. And this is to be substituted here. Instead of meter, we'll write this. So thus, let me write 10 power minus 6. And then instead of meter, 10 power plus 9. I may omit plus in this case, since it is one and the same, nanometer. So thus, we've got 10 power plus 3 nanometers. Regarding the number, original, length being 0.0034 micrometers. Same number to write in scientific notation. How to write it in scientific notation? A single non-zero digit is to the left of the decimal point, which means that this number is to be written 1, 2, 3 places. That's why 3.4 times 10 power minus 3 micrometers. Same number written in scientific notation. Now, micrometer substituted by its equal here, this one. So thus we will write the final result, 3.4 times 10 power minus 3 times 10 power 3. Just a moment. Times 10 power 3. And then what is this? Nanometers. And let me continue. They cancel. It is just 3.4 nanometers. This is the answer of that problem. So let us now have another example. You need just to practice. So not difficult at all. Just to practice. Let us take some area. Why? Because we've got unit squared to show this. For example, the area of an object, surface area, suppose, is 7,300 what? Let it be, just to look, let it be centimeters squared. Centimeters squared. And this to be changed into what unit? Femtometer squared. Some imaginary situation. Femtometer squared. How to change? So we'll begin initially with units, as usual. But since they're squared, let us start with the non-squared units. 1 centimeter, let us see how to change into femtometer. So 1 centimeter is, always we pass through the meter, being the base. So thus it is, centimeter is less unit than meter. That's right. It is 10 power minus 2 meters. But we don't need meter. Femtometer is needed. That's why we rewrite 10 power minus 2. And then this meter, 1 meter into femtometers, is 10 power plus 15 femtometers. Plus why? Because this is big, this is small. Positive exponent. So thus this must be substituted, this placed instead of meter, in the place of meter. So thus let me continue here, multiplied by 10 power 15 femtometers. So thus we've got 10 power 13 femtometers. Now let us, what to do? Take squared units. So we've got 10 power 13 femtometers squared. So first multiplier squared is 10 power 26 femtometers squared. So let us proceed with the original number. A is 7,300 squared centimeters. This in scientific notation. The understood decimal point shifted to the left, which makes 7.3 times 10. The number of the shifted place is 3, which means plus 3 squared centimeters. So the same number in scientific notation. This is the symbol for multiplication. Then we rewrite this part, 7.3 times 10 power 3. And then instead of centimeters squared, we'll write it's equal from the above. So that's multiplied by 10 power 26 femtometer squared. So thus the final result is 7.3 times 10 power 29 femtometers squared. So this not well located, this symbol. Let me write it properly in between the numbers. So, and this is the answer. So I think that this is enough for you. You need each one alone in front of the examples. Many examples here initially. Take this, so page 10. So many examples you can find here, but also as you see, you may invent any example alone and practice. Okay, so this is about prefix. I would like now to focus our attention on the scientific notation. This is very important in science. So let me switch on the presentation and see scientific notation, significant digit, figures. So in science, we deal with measured quantities, not pure numbers. So, for example, if you have to find some area, you need to multiply length times width. So that's why let me write length times width. So that's, let me take some length, 1.2 meters, some width, 0.3 meters. So that's the area being 1.2 meters times 0.3 meters is so you may use calculator quickly. I'll do it along as you like. So I purposely want to switch on the calculator to explain the difference between calculated quantities and measured quantities. So that's 1.2 multiplied by 0.36. Can't write this in this so in fact my example is very good, 0.36 meters squared, but we can't write in this way the answer. It is correct from mathematical point of view, but incorrect from the rules of significant digits. Why? Because those are measured quantities. So the way numbers are written shows the precision with which the experiment how the measurement was performed. So this 0.3 meter means that the device, the ruler used to measure it, has the precision within 0.1 of meter. And in this case, we've got two numbers to the right of the decimal point, which means precision within 100 of meters. That's why writing exactly what the calculator shows, in fact, changes the precision. That number is more precise than the multipliers. That's why there are rules to say us in what way to write the result. And the rules are given in the presentation, but also you can find in the red practice book also given. So let us focus on the rule. First rule, all non-zero figures are significant. This is okay. Second rule, about zeros, they may be significant or non-significant depending on the situation. In the second position, zeros between non-zero figures are significant. And example is given in which we've got, sorry for not having pointer, in which we've got a zero here between non-zero figures, which is significant, and two zeros between non-zero figures, also significant. So that all figures here are significant. That's why it is given 6 significant digits. Number 3, zeros to the right of a non-zero figure, those zeros to the right of a non-zero figure, but to the left of an understood, here which is understood decimal point, are never significant, which means that the mouse now, okay. So problems with the mouse, okay, which means that we've got 0 between 1 and 7. The 0 is significant according to the previous rule, but those 3 zeros after number 7 are not significant according to this very rule, unless, as given in the text, specifically indicated using that stroke above the number that are to be considered significant. Okay, so that's why this number has got 3 significant digits, those 107, but this number has got what? 5 significant figures, because those 2 zeros also are to be considered significant. So you may not understand exactly this very moment, but those rules must be applied constantly during the course when you perform different kinds of calculations. Then we've got number 4, all zeros to the right of a decimal point, to the right of the decimal point, those zeros, but to the left of a non-zero figure are not significant. So thus, if we have to discuss this number, we've got 4 significant digits. Those zeros cannot be considered significant. Then, number 5, all zeros, 2, those zeros are discussed, to the right of the decimal point, but following non-zero figure are significant. So that's why this 0 is not significant according to the previous rule. This is significant according to the second or third rule. And this also according to the rule 5. So thus we've got 4 significant digits. And we reached rule of addition and subtraction. So thus, Important here thing is the rightmost significant figure in a sum or difference depends on the leftmost place at which an uncertain figure occurs in any of the measurements being added. We will have example here, but let us complete with the previous example. Rule for multiplication. The product, shortly discussed, the product mustn't have more significant digits than, shouldn't have more significant digits or figures than the least precise factor. Let us come back now to the example. So we've got here length. The number of significant digits is 2. Why? Because all non-zero figures are significant. The number of significant figures here is 1, because this 0 is not significant. Then the product shouldn't have more significant figure than the least precise factor. Which is the least? Having smallest number of significant digits, this, which means that the product must have just 1 significant digits. That's why, how to write it now? How to write it as 1 significant digit? As 0.4 meter squared, or 4 times 10 power minus 1 meter squared in scientific notation. In case of addition and subtraction, if you needed to add those numbers, so the result would be, just the location of numbers must be same, 1.2. So thus we've got here 5, 1. So, but you see here the position of certain figure, the leftmost position of uncertain figure. The result is 1.5. This mustn't be written according to the rules of significant digits, because we've got a factor having just 1 digit to the right of the decimal point. So next time we will further practice this regarding significant digits, but please try to understand, read the rules, and at least learn how to apply them. And now I would like to discuss a bit the difference between precision and accuracy. So, precision and accuracy. Since if we deal with measured quantities, and since measurement contains error, we need to evaluate what is the degree of the uncertainty, not way to quantify uncertainty. And those terms are important to know. So in Bulgarian, for example, we don't have 2 different words for this. Quantifying uncertainty. But in English, there are exactly specified ways to express the difference. So, precision really shows consistency of data obtained after measuring many times one and the same thing. For example, you measure mass of a ball 10 times, and always case, there are very small differences due to different factors which cannot be predicted and are avoidable. So that's that. The closer the results, more precise is the experiment in this way. So precision refers to the consistency of repeated measures. And in this case, see, all the results are very close. They are located in almost one space. That's why this is precise, but not accurate as compared to this, in which the precision is not, you see, different attempts. So we've got some diversity in location. And precision is not good, but they are closer to the central point, being the aim, being the true value. So that's why we've got here accurate experiment, more accurate as compared to this, but less precise. More precise, but less accurate. So that accuracy refers to the closeness of measurement to the truth of the accepted value for the specific physical quantity. And there is a way to evaluate accuracy. Accuracy is evaluated in two ways. What are they? We've got in terms of absolute error and in terms of relative error. Absolute error. Absolute error is defined as the actual difference between the measured value, the value which you obtain after measuring the quantity, and the accepted, the true value. Those straight lines, they show that only positive value is to be taken of the difference, irrespectively of the real result. The absolute value. That's why absolute error. Sometimes instead of EA, it is written delta x. Delta x being x minus x accepted. If you measure, for example, volume, absolute error can be written as delta V. And it is volume which you measure minus the true value of the volume. Relative error, E from error, R from relative, is the ratio between the absolute error, the most probable accepted value, times 100, and the result would be expressed in percent. That's why relative error is also called percentage error. Percentage error. So that we've got absolute error, having unit of the measured quantity, and relative error, which is measured in percent. And next time we will consider an example to understand better how to calculate absolute and relative error and evaluate it. So let me tell you, we will never discuss conversions in the lectures because we will need to study many other things. That's why it's your responsibility to learn and understand. Then I would like to tell everybody, since there were questions from students, can you use tablets or electronic devices during lectures? Please do not. Because this cannot be accepted as lecture knowledge. Since files may be transferred through the world, and nobody can understand who prepared or wrote this file. This is, use those things for yourself, but during the lecture, use notebooks, not separate sheet of paper, please. Notebook. Do not use separate sheet of paper and then stick. No. Notebook, please. These are my requirements. I know why. I asked you to do it. Have a nice week. See you next time when we will discuss the topic static and dynamic